What if the universe is expanding faster than we can comprehend, and the force driving it remains one of the greatest enigmas in science? Picture this, an invisible energy, so powerful that it shapes the fate of the cosmos, yet so elusive that even the brightest minds on Earth struggle to define it. This is the mystery of cosmic dark energy flow, a phenomenon that challenges everything we think we know about the universe, from the accelerating expansion of space to the strange anomalies in the cosmic microwave background. Dark energy holds the key to understanding the very fabric of reality. In this video, we'll dive into 25 mind-bending mysteries surrounding dark energy, each one more perplexing than the last. Why does the universe seem to be tearing itself apart? What role does dark energy play in the ultimate fate of everything we see? And could it be connected to forces beyond our current understanding of physics? Stay with us, because by the end of this journey, you'll not only uncover the secrets of dark energy, but also glimpse the profound questions that keep scientists awake at night. The universe is full of wonders, and dark energy might just be the most mysterious of them all. Let's explore. Now, let's take a closer look at the first mystery, the accelerating universe. Imagine staring at the night sky, thinking the stars and galaxies are moving away from us at a steady pace. But what if I told you that's not the whole story? In the late 1990s, astronomers made a groundbreaking discovery that turned our understanding of the cosmos upside down. They found that the universe isn't just expanding, it's expanding faster and faster over time. This revelation was so shocking that it earned the researchers the Nobel Prize in Physics in 2011. But how did they figure this out? The key lies in supernovas, the explosive deaths of massive stars. By studying a specific type of supernova called Type 1a, scientists could measure distances across the universe with incredible precision. What they discovered was that these supernovas were farther away than expected, meaning the space between galaxies was stretching at an increasing rate. This observation led to the proposal of dark energy, a mysterious force pushing the universe apart. But here's the twist: no one knows exactly what dark energy is. It's invisible, it's everywhere, and it makes up about 68% of the universe's total energy. The implications are staggering. If dark energy continues to dominate, the universe could keep expanding forever, growing colder and emptier as galaxies drift farther apart. This discovery not only reshaped our understanding of the cosmos, but also opened up a whole new set of questions. What is driving this acceleration, and how will it shape the ultimate fate of the universe? As we peel back the layers of this mystery, one thing becomes clear. The accelerating universe is just the beginning of our journey into the enigmatic world of dark energy. Next, we'll explore what dark energy might actually be, and why it's so hard to pin down. Now that we've seen how dark energy drives the universe's accelerating expansion, let's dive into the heart of the mystery. What exactly is dark energy? Despite decades of research, scientists still don't have a definitive answer. But they've proposed several intriguing theories to explain this elusive force. One of the leading ideas is the cosmological constant, a concept first introduced by Albert Einstein over a century ago. This theory suggests that dark energy is a property of space itself, a constant energy density that fills the vacuum of the universe. It's like an invisible, unchanging force that pushes everything apart. But here's the catch: while the cosmological constant fits many observations, it also raises a big question. Why is the energy density of empty space so small compared to what quantum physics predicts? This mismatch is one of the biggest unsolved problems in modern physics. Another possibility is quintessence, a dynamic form of dark energy that changes over time. Unlike the cosmological constant, quintessence isn't fixed. It could grow stronger or weaker as the universe evolves, almost like a cosmic field that ebbs and flows. Some scientists think this could explain why the universe's expansion rate seems to vary slightly over time. But quintessence is still just a theory, and we don't have any direct evidence to prove it exists. Then there's phantom energy, perhaps the most dramatic of all. This theory suggests that dark energy could become stronger over time, eventually tearing apart everything in the universe from galaxies to atoms in a catastrophic event known as the Big Rip. While it sounds like science fiction, phantom energy isn't entirely ruled out by current observations. However, like the other theories, it remains speculative. So why is it so hard to pin down what dark energy really is? Part of the challenge lies in its nature. Dark energy doesn't interact with light or matter in any way we can detect directly. It's invisible, intangible, and only reveals itself through its effects on the universe's expansion. This makes it incredibly difficult to study, but scientists aren't giving up. They're using powerful telescopes, advanced simulations, and even artificial intelligence to gather more clues. Each new discovery brings us a step closer to unraveling this cosmic enigma. As we continue our journey, the next mystery we'll explore is how the cosmic microwave background, the afterglow of the Big Bang, might hold secrets about dark energy's influence on the early universe. Now, let's turn our attention to the cosmic microwave background, or CMB, often called the afterglow of the Big Bang. This faint radiation fills the entire universe and offers a snapshot of what the cosmos looked like just 380,000 years after its birth. It's like a cosmic fingerprint, revealing the seeds of galaxies, clusters, and the large-scale structure we see today. But within this ancient light, there are peculiar anomalies that have puzzled scientists for decades, and some of these might hold clues about dark energy's role in shaping the early universe. One of the most intriguing anomalies is the cold spot, a region in the CMB that's significantly cooler than its surroundings. At first glance, it might seem like a minor detail, but this cold spot is far larger than what standard cosmological models predict. Some researchers believe it could be evidence of a cosmic void, a vast, nearly empty region of space where dark energy's repulsive force has pushed matter apart more aggressively than elsewhere. If true, this would suggest that dark energy's influence isn't uniform across the universe, but instead varies in ways we're only beginning to understand. Another anomaly lies in the distribution of temperature fluctuations across the CMB. While most of these fluctuations are consistent with the predictions of the Big Bang theory, there are subtle deviations that don't quite fit. For instance, certain large-scale patterns appear weaker than expected, as if something, perhaps dark energy, has subtly altered the way these structures formed. These irregularities could be a sign that dark energy was already at work in the early universe, subtly tweaking the cosmic landscape long before galaxies began to form. But why does the CMB matter so much in the search for dark energy? Think of it as a time capsule. The CMB captures the universe at a critical moment, just as it transitioned from a hot, dense plasma to a cooler, more transparent state. Any influence dark energy had during this period would leave an imprint on the CMB, offering us a unique window into its behavior billions of years ago. By studying these anomalies, scientists hope to uncover whether dark energy has always been constant, as the cosmological constant suggests, or if it has evolved over time, as theories like quintessence propose. Of course, these anomalies aren't easy to interpret. They could be signs of dark energy's influence, or they might point to entirely new physics we haven't yet imagined. Either way, the CMB remains one of our most powerful tools for probing the mysteries of dark energy. As we continue to map its subtle variations with ever greater precision, we inch closer to understanding how this enigmatic force has shaped and continues to shape the universe we call home. Next, we'll explore another cosmic puzzle, the Hubble tension, and how it might be connected to the mysteries of dark energy. Now, shifting our gaze to another cosmic conundrum, let's dive into the Hubble tension, a puzzle that has left astronomers scratching their heads. At its core, the Hubble tension revolves around a simple yet profound question: how fast is the universe expanding? You'd think this would be straightforward to answer, but here's the twist: different methods of measuring this expansion rate, known as the Hubble constant, are giving us conflicting results. It's like having two clocks that should tell the same time but are ticking at different speeds. On one hand, we have measurements based on the cosmic microwave background, or CMB, which provide a snapshot of the early universe. These measurements suggest a specific value for the Hubble constant. On the other hand, observations of nearby objects like Cepheid variable stars and supernova give us a different value, one that's noticeably higher. This discrepancy isn't just a minor glitch, it's a significant gap that challenges our understanding of the cosmos. If both methods are accurate, why don't they agree? Could dark energy be the missing piece of this puzzle? One possibility is that dark energy isn't as constant as we've assumed. If its strength has changed over time, it could subtly alter the expansion rate of the universe in ways we haven't fully accounted for. For instance, if dark energy was weaker in the past and has grown stronger over billions of years, it might explain why the early universe's expansion rate, as seen in the CMB, differs from the rate we observe today. This idea ties back to theories like quintessence, which propose that dark energy evolves rather than remaining static. Another angle involves the way we measure distances in the universe. The Hubble constant relies on precise measurements of how far away objects are, and even small errors in these distances can lead to big discrepancies in the expansion rate. Could there be something we're missing in our calculations, perhaps an unseen factor influenced by dark energy? Some researchers speculate that dark energy's effects on the large-scale structure of the universe might be skewing our measurements in ways we don't yet understand. The Hubble tension isn't just a technical problem, it's a window into the deeper mysteries of the cosmos. Resolving it could shed light on the nature of dark energy, the evolution of the universe, and even the fundamental laws of physics. As scientists refine their measurements and develop new techniques, they're inching closer to an answer. But for now, the tension remains a tantalizing reminder of how much we still have to learn about the universe. As we move forward, let's explore another fascinating aspect of dark energy's influence: the fate of the universe. Could dark energy determine whether our cosmos ends in a big rip, a big crunch, or something entirely different? The answers might surprise you. Now, let's turn our attention to one of the most profound questions in cosmology: the fate of the universe. What lies ahead for our cosmos, and how does dark energy shape its ultimate destiny? The answer isn't straightforward, but scientists have proposed several compelling scenarios, each with dramatic implications for the future of everything we know. One possibility is the Big Rip. Imagine a universe where dark energy grows stronger over time, eventually overpowering all other forces. In this scenario, dark energy would accelerate the expansion of the universe so rapidly that it tears apart galaxies, stars, and even atoms themselves. It's a chilling thought, a universe unraveling at its seams, ending not with a bang, but with a violent, unstoppable expansion. This scenario hinges on the idea that dark energy isn't constant but instead intensifies as the universe ages, a concept tied to theories like phantom energy. On the other end of the spectrum lies the Big Crunch. Here, dark energy weakens over time, allowing gravity to take the reins. In this scenario, the universe's expansion slows, stops, and eventually reverses. Galaxies would begin to collapse inward, pulling closer and closer until everything is compressed into an infinitely dense point, a cosmic mirror of the Big Bang. This cyclical view of the universe suggests that expansion and contraction could be part of an endless loop, with each cycle birthing a new universe from the ashes of the old. Then there's the heat death, or the Big Freeze. In this scenario, dark energy maintains a steady influence, causing the universe to expand forever. but at a slower, more gradual pace. Over trillions of years, stars burn out, galaxies drift apart, and the universe grows colder and darker. Eventually, all energy is evenly distributed, and the cosmos reaches a state of maximum entropy, a lifeless, frozen expanse where nothing happens. It's a quiet, almost poetic end, but one that leaves no room for renewal or rebirth. These scenarios aren't just speculative fiction. They're grounded in our current understanding of dark energy and its behavior. If dark energy remains constant, the heat death seems the most likely outcome. But if it evolves, growing stronger or weaker over time, the universe's fate could swing dramatically toward the big rip or the big crunch. The challenge lies in determining which path dark energy will take, and that's where ongoing research comes in. By studying the expansion rate of the universe and the properties of dark energy, scientists hope to narrow down these possibilities and uncover the universe's ultimate destiny. As we ponder these cosmic futures, it's worth reflecting on what they mean for us. The fate of the universe isn't just an abstract concept. It's a reminder of the fleeting nature of existence and the vast, mysterious forces that shape our reality. And with that, let's explore another intriguing aspect of dark energy, its influence on the large-scale structure of the universe and how it shapes the cosmic web of galaxies and voids. Now, shifting our gaze to the grand tapestry of the cosmos, let's explore how dark energy shapes the large-scale structure of the universe. On the largest scales, the universe isn't just a random scattering of galaxies. It's a vast, intricate web of filaments, clusters, and voids. This cosmic web is the result of billions of years of gravitational interactions, but dark energy plays a crucial role in how it forms and evolves. At the heart of this structure are galaxy clusters, the most massive objects in the universe bound together by gravity. These clusters are connected by long, thread-like filaments of galaxies, gas, and dark matter, creating a network that spans billions of light years. Between these filaments lie enormous voids, regions of space that are almost entirely empty, stretching across hundreds of millions of light years. It's here, in these vast voids, that dark energy's influence becomes most apparent. As the universe expands, dark energy pushes galaxies and galaxy clusters apart, stretching the cosmic web over time. In regions where matter is dense, like galaxy clusters, gravity still dominates, holding these structures together. But in the voids where matter is sparse, dark energy's repulsive force has a much stronger effect. It accelerates the expansion of these empty regions, causing them to grow larger and emptier over time. This creates a feedback loop. As voids expand, they pull matter away from the surrounding filaments, further thinning out the cosmic web. This dynamic interplay between gravity and dark energy shapes the universe on the largest scales. Without dark energy, the cosmic web would look very different. Galaxies would be more tightly packed, and voids would be smaller and less pronounced. But with dark energy driving the expansion, the universe becomes a patchwork of dense clusters and vast, empty expanses, a structure that reflects the delicate balance between these two opposing forces. What's fascinating is that this large-scale structure isn't just a snapshot of the universe today. It's a record of its history. By studying the distribution of galaxies and the growth of voids, scientists can trace how dark energy has influenced the universe over billions of years. This helps us understand not only where we are in the cosmos, but also how we got here and where we might be headed. As we continue to map the universe's structure, new questions arise. How exactly does dark energy interact with dark matter, the invisible scaffolding that holds galaxies together? And what does the evolution of the cosmic web tell us about the future of the universe? These are the mysteries that drive astronomers and cosmologists to peer deeper into the cosmos, unraveling the secrets of dark energy one observation at a time. And with that, let's turn our attention to another intriguing aspect of this cosmic puzzle, the role of the quantum vacuum in shaping the universe's expansion. Now, let's venture into one of the most intriguing and debated ideas in modern cosmology: the role of the quantum vacuum in the mystery of dark energy. At first glance, empty space might seem like nothingness, but in the realm of quantum physics, it's anything but empty. Instead, it's a seething, dynamic arena filled with fleeting particles and energy fluctuations. This so-called quantum vacuum is thought to hold the key to understanding dark energy, but it's a puzzle that challenges even the brightest minds in science. The quantum vacuum is the lowest possible energy state of space, yet it's far from inert. According to quantum mechanics, particles and antiparticles constantly pop in and out of existence, creating a background energy that permeates the universe. This energy, often referred to as zero-point energy, is a fundamental feature of the quantum world. Some scientists propose that this energy could be the source of dark energy, driving the accelerated expansion of the universe. If true, it would mean that the very fabric of space itself is responsible for one of the greatest mysteries in cosmology. But here's where things get controversial. When physicists calculate the energy density of the quantum vacuum using quantum field theory, they arrive at a number that's staggeringly large, so large, in fact, that it should have caused the universe to expand at an unimaginable rate, tearing apart galaxies, stars, and even atoms in an instant. Yet, observations show that dark energy's effect is far weaker, almost imperceptibly so. This discrepancy, known as the cosmological constant problem, is one of the biggest unsolved puzzles in physics. Why is the observed value of dark energy so much smaller than what quantum theory predicts? No one knows for sure, and this gap between theory and observation has led to intense debate and speculation. Some researchers suggest that there might be a cancellation mechanism at play, where positive and negative contributions to the vacuum energy somehow balance out, leaving only a tiny residual effect that we observe as dark energy. Others propose entirely new physics, such as modifications to quantum field theory or the existence of hidden dimensions, to explain the discrepancy. These ideas are fascinating but remain speculative, highlighting just how much we still have to learn about the quantum vacuum and its connection to dark energy. What makes this concept so compelling is its potential to unify two of the most profound areas of physics, quantum mechanics and cosmology. If dark energy truly arises from the quantum vacuum, it would bridge the microscopic world of particles with the macroscopic structure of the universe. Yet, until we can reconcile the theoretical predictions with observational evidence, the quantum vacuum remains a tantalizing but elusive piece of the dark energy puzzle. As we continue to explore this idea, one thing is clear: the quantum vacuum challenges our understanding of space, energy, and the very nature of reality. It's a reminder that even the emptiest regions of the universe are teeming with mystery, waiting to be unraveled. And with that, let's turn our attention to another profound question: why the predicted value of the cosmological constant differs so drastically from what we observe, and what this means for our understanding of the cosmos. Now, shifting our focus to one of the most perplexing challenges in modern physics, we arrive at the cosmological constant problem. This issue lies at the heart of our struggle to understand dark energy and its role in the universe. The cosmological constant, first introduced by Albert Einstein, was originally meant to describe a static universe. Though Einstein later abandoned the idea, it resurfaced as a potential explanation for dark energy. But here's the catch: the predicted value of the cosmological constant, based on quantum field theory, is astronomically larger than what we observe in the universe. In fact, the theoretical value is around 120 orders of magnitude greater than the observed value. To put it simply, this discrepancy is like predicting a mountain but finding only a grain of sand. So, why does this gap exist? The answer lies in the way we calculate the energy of the quantum vacuum. According to quantum mechanics, empty space isn't truly empty. It's filled with virtual particles that constantly appear and disappear, contributing to what's known as vacuum energy. When physicists sum up all these contributions, they arrive at an enormous energy density. But when we look at the universe, the effect of dark energy is incredibly subtle, barely nudging the cosmos apart. This mismatch between theory and observation is what makes the cosmological constant problem so baffling. One possible explanation is that there's a cancellation mechanism at work, where positive and negative contributions to the vacuum energy somehow balance each other out, leaving behind only a tiny residual effect. Think of it like a tug of war where both sides are equally strong, resulting in almost no movement. However, this idea is purely speculative, and no one has yet figured out how such a mechanism would operate. Another possibility is that our understanding of quantum field theory is incomplete, and we're missing a crucial piece of the puzzle. Some scientists even suggest that entirely new physics beyond our current models might be needed to resolve this issue. The cosmological constant problem isn't just a technical challenge, it's a profound mystery that touches on the very nature of reality. It forces us to question whether our theories are missing something fundamental, or if there's a deeper layer of the universe we've yet to uncover. This problem also highlights the tension between quantum mechanics and general relativity, two of the most successful theories in physics which still refuse to fully align. As we grapple with this enigma, one thing is certain: solving the cosmological constant problem could revolutionize our understanding of the universe. It might reveal new insights into the nature of dark energy, the fabric of space-time, and even the origins of the cosmos itself. Until then, this problem remains one of the greatest unsolved mysteries in science, a testament to how much we still have to learn about the universe we call home. And with that, let's turn our attention to another fascinating aspect of dark energy: how its influence might change over time, shaping the past, present, and future of the cosmos. Now, let's take a step forward and explore how dark energy's influence might evolve over time, shaping the universe's expansion in ways we're only beginning to understand. One of the most intriguing questions in cosmology is whether dark energy has always behaved the same way, or if its effects have changed as the universe has aged. To answer this, we need to look back in time, examining how the cosmos has expanded over billions of years. In the early universe, gravity dominated the scene, pulling matter together and slowing down the expansion. But as the universe grew larger and matter spread out, gravity's grip weakened. This is when dark energy began to take center stage, pushing galaxies apart and accelerating the expansion. Observations of distant supernova and the cosmic microwave background suggest that dark energy's influence became significant around 5 billion years ago. But here's the twist: we don't know if this influence has remained constant or if it's been changing over time. Some theories propose that dark energy's strength could vary, growing stronger or weaker as the universe evolves. For instance, if dark energy were to increase over time, it could lead to a scenario known as the Big Rip, where the universe tears itself apart. On the other hand, if dark energy were to weaken, the expansion might slow down, potentially allowing gravity to regain control. This uncertainty makes studying dark energy's behavior over time one of the most critical challenges in modern cosmology. To understand this better, scientists are using tools like the Hubble Space Telescope and upcoming missions like the Euclid Telescope to measure the universe's expansion rate with unprecedented precision. By comparing how fast the universe is expanding now to how fast it expanded in the past, we can piece together a timeline of dark energy's influence. These observations could reveal whether dark energy is truly constant or if it's been changing, offering clues about the universe's ultimate fate. But the implications go even deeper. If dark energy's influence has changed over time, it could mean that our understanding of the fundamental forces of nature is incomplete. It might hint at new physics beyond our current theories that could reshape our view of the cosmos. For now, though, dark energy's relationship with time remains one of the most tantalizing mysteries in science, a puzzle that could hold the key to understanding not just the universe's past and present, but its future as well. As we continue to unravel this mystery, one thing is clear: the story of dark energy is far from over. Its influence over time could redefine our understanding of the universe from its earliest moments to its distant future. And with that, let's turn our attention to another fascinating possibility. What if dark energy isn't constant at all, but grows stronger over time? This idea, known as the phantom energy hypothesis, could lead to one of the most dramatic scenarios in cosmology, the Big Rip. Now, let's dive into one of the most dramatic possibilities in the study of dark energy, the phantom energy hypothesis. Imagine a force that doesn't just push the universe apart, but grows stronger as time goes on, eventually becoming so powerful that it could tear everything apart. This is the essence of phantom energy, a theoretical form of dark energy that could lead to a cosmic catastrophe known as the Big Rip. Unlike the cosmological constant, which suggests dark energy remains steady over time, phantom energy proposes that dark energy's influence increases as the universe expands. This means that the acceleration of the universe's expansion wouldn't just continue, it would speed up exponentially. Over time, this relentless force could overcome even the strongest bonds in the universe, from galaxies and stars to atoms and subatomic particles. In the end, nothing would be left intact. The idea of phantom energy raises profound questions about the nature of dark energy itself. If it's not constant, what causes it to grow stronger? Some theories suggest that phantom energy could be tied to exotic forms of matter or fields that behave in ways we don't yet understand. Others propose that it might be connected to the quantum vacuum, the energy of empty space, but with properties far stranger than we've ever imagined. What makes this hypothesis so compelling is its potential to explain some of the most puzzling observations in cosmology. For instance, if phantom energy is real, it could account for discrepancies in measurements of the universe's expansion rate. It might also provide clues about the ultimate fate of the cosmos, offering a glimpse into a future where the universe doesn't just fade away but is violently torn apart. Of course, the phantom energy hypothesis is still speculative, and there's no direct evidence to confirm it yet, but scientists are actively searching for clues. Observations of distant supernova, the cosmic microwave background, and the large-scale structure of the universe could all provide hints about whether dark energy is constant or growing stronger. Upcoming missions like the Euclid telescope and the Vera Rubin Observatory are expected to shed new light on this mystery, potentially bringing us closer to understanding whether phantom energy is real. The implications of this hypothesis are staggering. If phantom energy exists, it would mean that the universe's fate is far more dramatic than we've ever imagined. Instead of a slow, cold end, the cosmos could face a violent and sudden demise. But even if phantom energy turns out to be just a fascinating idea, exploring it pushes the boundaries of our understanding, challenging us to rethink the fundamental forces that shape the universe. As we ponder the possibilities of phantom energy, let's shift our focus to another intriguing aspect of dark energy, its potential connection to gravitational waves. Could these ripples in space-time hold the key to unlocking more secrets about dark energy's mysterious nature? Now, let's turn our attention to another fascinating avenue in the study of dark energy, its potential connection to gravitational waves. These ripples in space-time, first predicted by Einstein over a century ago, have opened up a whole new way of observing the universe. But what do they have to do with dark energy? As it turns out, gravitational waves could hold the key to unraveling some of the deepest mysteries surrounding this enigmatic force. Gravitational waves are created by some of the most violent and energetic events in the cosmos, such as the collision of black holes or the merging of neutron stars. When these massive objects collide, they send out ripples that travel across the universe, distorting space-time itself. By detecting these ripples, scientists can learn not only about the objects that created them, but also about the fabric of the universe they've traveled through. This is where dark energy comes into play. One of the most promising ways gravitational waves could shed light on dark energy is through their ability to measure distances in the universe. When two neutron stars merge, they produce both gravitational waves and a burst of light, known as a kilonova. By comparing the distance measured from the gravitational waves with the distance inferred from the light, scientists can get a more precise measurement of how fast the universe is expanding. This, in turn, can help refine our understanding of dark energy's influence on cosmic expansion. But that's not all. Gravitational waves could also reveal how dark energy behaves over time. For example, if dark energy's strength changes as the universe expands, it could subtly alter the way gravitational waves propagate through space. By studying these subtle changes, scientists might be able to detect whether dark energy is constant, as the cosmological constant suggests, or whether it evolves, as theories like phantom energy propose. Another intriguing possibility is that gravitational waves could help us map the large-scale structure of the universe. Dark energy plays a crucial role in shaping this structure, influencing how galaxies and galaxy clusters form and evolve. By observing how gravitational waves are affected by the distribution of matter and energy in the universe, scientists could gain new insights into how dark energy operates on the largest scales. Of course, this field of research is still in its early stages. Detecting gravitational waves is an incredibly challenging task, requiring some of the most sensitive instruments ever built, like the Laser Interferometer Gravitational Wave Observatory, or LIGO. But as technology advances and more gravitational wave events are detected, the potential for groundbreaking discoveries grows. Upcoming observatories like the Einstein Telescope and the Laser Interferometer Space Antenna, or LISA, promise to take this research to new heights, offering even more precise measurements and a deeper understanding of dark energy. The connection between dark energy and gravitational waves is a perfect example of how different areas of science can come together to solve some of the universe's biggest mysteries. By combining observations from gravitational waves with data from other sources, like the cosmic microwave background and supernova, scientists are piecing together a more complete picture of dark energy and its role in shaping the cosmos. As we continue to explore this exciting frontier, let's shift our focus to another intriguing aspect of dark energy, its relationship with dark matter. How do these two mysterious components of the universe interact, and what does their interplay mean for the cosmos? Now, let's dive into another layer of cosmic mystery, the relationship between dark energy and dark matter. These two invisible forces dominate the universe, yet they couldn't be more different in how they behave. Dark matter, unlike dark energy, doesn't push the universe apart, it pulls things together. It acts like a cosmic glue, holding galaxies and galaxy clusters in place through its gravitational pull. But how do these two mysterious components interact, and what does their interplay mean for the structure and evolution of the universe? To understand this, let's start with dark matter. While we can't see it directly, we know it exists because of its gravitational effects. Without dark matter, galaxies would fly apart, and the universe as we know it wouldn't exist. It's the scaffolding that holds the cosmos together, shaping the large-scale structure of the universe. But here's where things get interesting. Dark energy, on the other hand, is working against dark matter. While dark matter pulls, dark energy pushes, driving the accelerated expansion of the universe. This cosmic tug of war is at the heart of how the universe evolves. One of the most fascinating aspects of this relationship is how it influences the formation of cosmic structures. In the early universe, dark matter's gravitational pull caused matter to clump together, forming the seeds of galaxies and galaxy clusters. But as the universe expanded, dark energy began to dominate, slowing down the growth of these structures. Today, dark energy is causing the universe to expand faster and faster, stretching the fabric of space-time and making it harder for new structures to form. This delicate balance between dark matter and dark energy has shaped the universe we see today, but the interplay between these two forces doesn't stop there. Scientists believe that dark matter and dark energy might be connected in ways we don't yet fully understand. Some theories suggest that dark energy could be a property of dark matter itself, or that the two might interact in subtle ways that we haven't detected yet. For example, if dark energy's strength changes over time, it could affect how dark matter behaves, altering the way galaxies form and evolve. This possibility opens up a whole new realm of questions about the nature of these mysterious forces. Another intriguing idea is that dark matter and dark energy might be two sides of the same coin. Some theories propose that they could be different manifestations of a single underlying phenomenon. If this is true, it could revolutionize our understanding of the universe, providing a unified explanation for both the structure and expansion of the cosmos. While this remains speculative, it highlights just how much we still have to learn about these fundamental components of the universe. As we continue to explore the mysteries of dark matter and dark energy, one thing is clear: their interplay is crucial to understanding the universe's past, present, and future. By studying how these forces shape the cosmos, scientists are piecing together a more complete picture of the universe's evolution. And as new technologies and observatories come online, we're getting closer to uncovering the secrets of these invisible forces that govern everything we see and don't see. With this in mind, let's turn our attention to another captivating idea: the possibility that dark energy might be connected to the existence of a multiverse. Could our universe be just one of many? And if so, what does that mean for dark energy's role in the grand scheme of things? Now, let's venture into one of the most mind-bending ideas in modern cosmology: the possibility that dark energy might be connected to the existence of a multiverse. Imagine for a moment that our universe is just one of countless others, each with its own unique set of physical laws and constants. This idea, known as the multiverse theory, has gained traction in recent years, and it might hold the key to understanding why dark energy behaves the way it does. At the heart of this connection is the concept of fine-tuning. Dark energy's value, as we observe it, seems perfectly calibrated to allow for the existence of galaxies, stars, and ultimately, life. But why is this the case? One explanation is that in a multiverse, every possible value of dark energy exists somewhere. In most universes, dark energy might be too weak or too strong to allow for the formation of complex structures. But in a rare few, like ours, it's just right. This idea, often tied to the anthropic principle, suggests that we live in a universe where dark energy's properties are ideal for our existence simply because we're here to observe it. But the multiverse connection goes even deeper. Some theories propose that dark energy could be a byproduct of interactions between our universe and others. For instance, if our universe is one bubble in a vast cosmic foam of universes, dark energy might arise from the energy exchange between these bubbles. This could explain why dark energy seems to permeate all of space, driving the universe's expansion in a way that feels almost like a cosmic pressure from beyond our own reality. Another intriguing possibility is that dark energy's behavior could be influenced by the gravitational pull of neighboring universes. If our universe is part of a larger multiverse, the gravitational effects of nearby universes might subtly alter how dark energy operates within our own. This could provide a natural explanation for why dark energy's strength appears to change over time, a phenomenon that remains one of the biggest mysteries in cosmology. Of course, these ideas are highly speculative, and testing them is no easy task. The multiverse, by its very nature, lies beyond the reach of our current observational tools. But that hasn't stopped scientists from exploring creative ways to look for evidence. For example, some researchers are investigating whether the cosmic microwave background, the afterglow of the Big Bang, might contain subtle imprints of collisions between our universe and others. Others are studying the large-scale structure of the universe, searching for patterns that could hint at the influence of a multiverse. While the multiverse remains a theoretical concept, it offers a fascinating framework for thinking about dark energy's mysterious properties. If true, it could mean that dark energy isn't just a feature of our universe, it's a consequence of a much larger, more complex cosmic reality. And as we continue to probe the mysteries of dark energy, the multiverse connection reminds us that the answers we seek might lie far beyond the boundaries of what we can currently observe. With this in mind, let's shift our focus to another profound question. Could dark energy's value be fine-tuned to allow for the existence of life? This idea, known as the anthropic principle, raises fascinating philosophical and scientific questions about our place in the cosmos. Now, let's turn our attention to a concept that bridges science and philosophy, the anthropic principle. This idea suggests that the value of dark energy might be precisely fine-tuned to allow for the existence of life as we know it. At first glance, this might sound like a coincidence, but when you dig deeper, it raises profound questions about the nature of our universe and our place within it. The anthropic principle comes in two main forms, the weak and the strong. The weak anthropic principle simply states that the conditions we observe in the universe must be compatible with our existence as observers. In other words, if dark energy were significantly stronger or weaker, galaxies, stars, and planets might never have formed, making life impossible. This doesn't explain why dark energy has the value it does, but it does highlight how uniquely suited our universe seems to be for life. The strong anthropic principle takes this idea a step further, proposing that the universe must have properties that allow life to arise at some point in its history. This version of the principle often leads to more speculative discussions, including the possibility of a multiverse, where countless universes exist with different physical constants. In this scenario, we happen to live in one of the rare universes where dark energy's value is just right for life to emerge. But why does dark energy's value matter so much? If dark energy was stronger, the universe would have expanded too quickly for galaxies to form. If it were weaker, gravity might have caused the universe to collapse back on itself long before life could evolve. The fact that dark energy's value seems so finely balanced has led some scientists and philosophers to wonder whether this is mere chance or evidence of something deeper. This brings us to the philosophical implications of the anthropic principle. If the universe is fine-tuned for life, does that imply the existence of a cosmic designer? Or is it simply a result of the multiverse, where every possible configuration of physical constants exists somewhere? These questions touch on the very nature of reality and our understanding of existence. While science doesn't provide definitive answers, the anthropic principle invites us to consider the possibility that our universe is not just a random accident but part of a much larger, perhaps even intentional, cosmic framework. Some critics argue that the anthropic principle is a tautology. It explains nothing because it simply states the obvious. We exist, so the universe must allow for our existence. Others see it as a valuable tool for guiding scientific inquiry, helping us focus on why certain constants like dark energy have the values they do. Regardless of where you stand, the anthropic principle challenges us to think deeply about the nature of the cosmos and our role within it. As we ponder these questions, let's shift our gaze to another intriguing possibility. Could dark energy's effects be amplified in the vast, empty regions of space known as cosmic voids? This idea, known as the void hypothesis, offers a fresh perspective on how dark energy might shape the universe on the largest scales. Now, let's venture into one of the most fascinating ideas in modern cosmology, the void hypothesis. This theory suggests that dark energy's influence might be most pronounced in the vast, empty regions of space known as cosmic voids. These voids, which make up a significant portion of the universe, are enormous areas where matter is sparse, often spanning hundreds of millions of light years. But why would dark energy behave differently in these regions, and what does this mean for our understanding of the cosmos? To grasp this concept, imagine the universe as a cosmic web, with galaxies and galaxy clusters forming dense filaments and walls, while the voids are the empty spaces in between. These voids aren't just empty, they're dynamic regions where the effects of dark energy could be amplified. Some scientists propose that the accelerated expansion of the universe might be more noticeable in these areas because there's less matter to counteract dark energy's repulsive force. In other words, where gravity's pull is weakest, dark energy's push might dominate. This idea could help explain certain observational anomalies that have puzzled astronomers. For instance, measurements of the universe's expansion rate sometimes vary depending on where and how they're taken. If dark energy's effects are stronger in voids, it could mean that our observations are influenced by the specific regions we're studying. This would add a new layer of complexity to our understanding of cosmic expansion and dark energy's role in shaping the universe. The void hypothesis also raises intriguing questions about the large-scale structure of the cosmos. If dark energy's influence is uneven, it could mean that the universe isn't expanding uniformly. Instead, some regions might be stretching faster than others, leading to a more dynamic and varied cosmic landscape. This challenges the traditional view of a smooth, homogeneous universe and opens the door to new ways of thinking about how dark energy interacts with space and time. But how do we test this idea? One approach is to study the distribution of galaxies and voids in greater detail. By mapping the universe's large-scale structure, astronomers can look for patterns that might reveal how dark energy behaves in different environments. Projects like the Dark Energy Survey and the upcoming Euclid mission are designed to do just that, using advanced telescopes to peer deeper into the cosmos than ever before. These observations could provide crucial evidence for or against the void hypothesis, helping us refine our understanding of dark energy's mysterious nature. As we explore this hypothesis, it's worth considering its broader implications. If dark energy's effects are indeed amplified in voids, it could mean that our universe is far more complex and varied than we once thought. It might also hint at deeper connections between dark energy, gravity, and the fundamental forces that govern the cosmos. While the void hypothesis is still speculative, it represents an exciting frontier in our quest to unravel the mysteries of dark energy and the universe itself. With this in mind, let's turn our attention to another compelling idea: the role of modified gravity as an alternative explanation for the phenomena we attribute to dark energy. Could it be that our understanding of gravity itself needs to be rethought? Now, shifting our focus to another intriguing possibility, let's explore the idea that our understanding of gravity itself might need a rethink. This brings us to the role of modified gravity, a theory that challenges the need for dark energy altogether. Instead of attributing the universe's accelerated expansion to an unknown force, some scientists propose that gravity might behave differently on cosmic scales than we currently believe. One of the most well-known examples of this is modified Newtonian dynamics, or MUND for short. MUND suggests that at extremely large distances, the force of gravity doesn't follow the same rules as it does on smaller scales, like within our solar system. Instead of weakening with distance as Newton's laws predict, gravity might weaken more slowly, creating the illusion of an accelerating universe. This idea emerged as a way to explain why galaxies rotate faster than expected without invoking dark matter, but it has since been extended to address the cosmic expansion attributed to dark energy. However, modified gravity theories like MUND face significant challenges. For one, they struggle to explain all the observations that dark energy accounts for, such as the precise measurements of the cosmic microwave background and the large-scale distribution of galaxies. Additionally, these theories often require introducing new parameters or assumptions, which some critics argue make them less elegant than the dark energy hypothesis. Despite these hurdles, modified gravity remains a compelling alternative, pushing scientists to question and refine our fundamental understanding of the universe. One of the key debates surrounding modified gravity is whether it can truly replace dark energy or if it merely shifts the mystery to a different set of questions. For example, if gravity behaves differently on cosmic scales, what causes this change? Is there a deeper, yet to be discovered principle at work? These questions highlight the complexity of the issue and the need for more data to resolve the debate. Efforts to test modified gravity are ongoing, with researchers using observations from galaxy clusters, gravitational lensing, and even the motion of stars within galaxies to look for deviations from standard gravitational behavior. While no definitive evidence has yet emerged to overturn our current understanding, the pursuit of these theories keeps the scientific community on its toes, constantly re-evaluating and challenging established ideas. As we consider the role of modified gravity, it's worth reflecting on the broader implications. If gravity does behave differently on cosmic scales, it could revolutionize not just cosmology but our entire understanding of physics. It might even hint at a deeper connection between gravity and the other fundamental forces of nature, opening the door to a more unified theory of the universe. While the debate between dark energy and modified gravity remains unresolved, it's a testament to the dynamic and ever-evolving nature of science. With this in mind, let's turn our attention to another groundbreaking effort in the search for answers, the Dark Energy Survey, a massive project designed to map the universe's expansion and shed light on the mysteries of dark energy. Now, let's dive into one of the most ambitious scientific endeavors of our time, the Dark Energy Survey. This groundbreaking project represents a massive collaborative effort to map the universe's expansion with unprecedented precision, offering new insights into the mysterious properties of dark energy. By observing hundreds of millions of galaxies, the survey aims to uncover clues about how dark energy has influenced the cosmos over billions of years. The Dark Energy Survey, often abbreviated as DES, uses a powerful telescope equipped with a state-of-the-art camera capable of capturing detailed images of distant galaxies. Over the course of its observations, the survey has collected an enormous amount of data, allowing scientists to study the distribution of galaxies, the bending of light due to gravitational lensing, and the large-scale structure of the universe. These observations are crucial for testing theories about dark energy and its role in shaping the cosmos. One of the key goals of the Dark Energy Survey is to measure the rate of the universe's expansion over time. By analyzing how galaxies are distributed across vast distances, researchers can trace the influence of dark energy and determine whether its strength has remained constant or changed over cosmic history. This information could help resolve some of the biggest questions in cosmology, such as the nature of dark energy and its ultimate impact on the fate of the universe. The survey has already produced remarkable results, including detailed maps of galaxy clusters and the discovery of new supernova, which serve as cosmic mile markers for measuring distances in the universe. These findings have provided valuable data for testing competing theories, from the cosmological constant to modified gravity, and have helped refine our understanding of the universe's evolution. However, the Dark Energy Survey is just one piece of a much larger puzzle. Its findings are being combined with data from other projects, such as the Planck satellite's measurements of the cosmic microwave background and observations from the Hubble Space Telescope. Together, these efforts are painting a more complete picture of the cosmos, bringing us closer to unraveling the mysteries of dark energy. As we look to the future, the Dark Energy Survey serves as a testament to the power of collaboration and innovation in science. It reminds us that solving the universe's greatest mysteries requires not only cutting-edge technology, but also the collective effort of researchers from around the world. With each new discovery, we inch closer to understanding the forces that shape our universe and our place within it. With this in mind, let's turn our attention to another fascinating aspect of dark energy research: the potential connection between supermassive black holes and the mysterious force driving the universe's expansion. Now, shifting our focus to the cosmos' most enigmatic giants, let's explore the intriguing possibility that supermassive black holes might hold clues to the nature of dark energy. These colossal objects found at the centers of galaxies are not just gravitational powerhouses but could also play a surprising role in the universe's accelerating expansion. Supermassive black holes are known for their immense gravitational pull, capable of devouring stars and even entire galaxies. But recent research suggests their influence might extend far beyond their immediate surroundings. Some scientists propose that the growth of supermassive black holes over cosmic time could be linked to the behavior of dark energy. As these black holes accumulate mass, they might release energy or interact with the fabric of spacetime in ways that contribute to the universe's expansion. One theory suggests that the energy released by supermassive black holes during their growth phases could act as a counterbalance to dark energy's repulsive force. Alternatively, the sheer density of matter around these black holes might create localized distortions in spacetime, influencing how dark energy operates on larger scales. While these ideas are still speculative, they open up exciting avenues for understanding the interplay between the universe's most massive objects and its most mysterious force. Observations of supermassive black holes in distant galaxies have revealed that their growth rates align with periods of cosmic expansion. This correlation has led researchers to wonder whether black holes and dark energy are part of a larger cosmic feedback loop. For instance, as galaxies merge and their central black holes collide, the resulting energy output could subtly alter the rate of expansion in their vicinity. Over billions of years, these small changes might add up, shaping the universe's overall evolution. However, the connection between supermassive black holes and dark energy remains a topic of intense debate. Some argue that the influence of black holes is too localized to affect the universe on a grand scale, while others believe their cumulative impact could be significant. To resolve this question, scientists are combining data from black hole observations with measurements of cosmic expansion, hoping to uncover patterns that reveal a deeper relationship. As we continue to probe the mysteries of supermassive black holes, their potential link to dark energy offers a tantalizing glimpse into the interconnected nature of the cosmos. Whether they are key players in the universe's expansion or simply cosmic bystanders, these giants remind us that even the most massive objects in existence are part of a delicate cosmic dance. With this in mind, let's turn our attention to another piece of the puzzle: how dark energy might have behaved differently in the early universe and what that could mean for our understanding of cosmic history. Now, let's journey back in time to the early universe, a period when the cosmos was a vastly different place. During this era, dark energy might have behaved in ways that challenge our current understanding. Exploring this possibility not only sheds light on the universe's infancy, but also helps us piece together how dark energy has shaped cosmic evolution over billions of years. In the early universe, matter was densely packed, and the forces at play were far more intense than they are today. Dark energy, which now drives the universe's accelerated expansion, might have had a much weaker influence back then. Some theories suggest that dark energy's effects were overshadowed by the dominance of radiation and matter, which dictated the universe's expansion rate during its first few billion years. This raises a fascinating question. If dark energy was less significant in the past, when and how did it become the dominant force we observe today? One intriguing idea is that dark energy's strength has evolved over time. Unlike the cosmological constant, which assumes dark energy remains unchanged, alternative models propose that it could have varied in response to the universe's changing conditions. For instance, during the early universe's rapid expansion, dark energy might have interacted differently with matter and radiation, leading to subtle shifts in its behavior. These shifts could explain why the universe transitioned from a matter-dominated era to one where dark energy reigns supreme. Observations of the cosmic microwave background, the afterglow of the Big Bang, provide some clues about dark energy's role in the early universe. Tiny fluctuations in this ancient light reveal how matter and energy were distributed shortly after the universe's birth. By studying these patterns, scientists can infer how dark energy might have influenced the universe's initial expansion and structure formation. Some anomalies in the cosmic microwave background, such as unexpected temperature variations, could hint at dark energy's early activity, though these remain topics of ongoing research. Another possibility is that dark energy's behavior in the early universe was tied to the formation of the first galaxies and stars. As matter clumped together under gravity, dark energy might have subtly altered the rate at which these structures formed. This interplay between dark energy and matter could have left imprints on the large-scale structure of the universe, which we can now observe through galaxy surveys and other astronomical tools. Understanding these imprints could help us reconstruct the timeline of dark energy's rise to dominance. However, piecing together dark energy's early history is no easy task. The further back in time we look, the fainter and more elusive the evidence becomes. To overcome this challenge, scientists are developing advanced telescopes and simulations that can peer deeper into the universe's past. Missions like the Euclid Space Telescope and the Vera Rubin Observatory aim to map the distribution of galaxies and dark matter with unprecedented precision, offering new insights into how dark energy has evolved over cosmic history. As we unravel the mysteries of dark energy's behavior in the early universe, we gain a clearer picture of how the cosmos has transformed over billions of years. This journey not only deepens our understanding of dark energy, but also connects us to the universe's origins, reminding us that the forces shaping our reality today have roots that stretch back to the dawn of time. With this in mind, let's turn our attention to another fascinating aspect of dark energy: the potential role of neutrinos, those elusive particles that might hold unexpected clues to the universe's expansion. Now, shifting our focus to the tiniest yet most enigmatic particles in the universe, let's explore the role of neutrinos in the grand puzzle of dark energy. Neutrinos, often called ghost particles, are nearly massless, electrically neutral particles that zip through space at incredible speeds, barely interacting with matter. Despite their elusive nature, these particles might hold surprising clues about the universe's expansion and the behavior of dark energy. One of the most intriguing aspects of neutrinos is their connection to the early universe. In the first moments after the Big Bang, neutrinos were among the most abundant particles, flooding the cosmos in vast numbers. As the universe expanded and cooled, these particles decoupled from matter, traveling freely through space. Their sheer abundance and unique properties mean they could have played a subtle but significant role in shaping the universe's evolution, potentially influencing how dark energy operates on cosmic scales. One key question scientists are exploring is whether neutrinos could interact with dark energy in ways we haven't yet detected. While neutrinos are known to interact weakly with matter, their potential interactions with dark energy remain a mystery. Some theories suggest that neutrinos might carry information about dark energy's influence on the universe's expansion, acting as cosmic messengers that reveal hidden dynamics. For instance, if dark energy's strength has changed over time, neutrinos might bear traces of these shifts in their behavior or distribution. Another fascinating possibility is that neutrinos themselves could contribute to dark energy. While neutrinos are incredibly light, their combined mass across the universe might have a small but measurable effect on cosmic expansion. If neutrinos have even a tiny amount of mass, as recent experiments suggest, their gravitational influence could subtly alter the rate at which the universe expands. This raises the tantalizing idea that neutrinos and dark energy might be intertwined in ways we're only beginning to understand. Observations of neutrinos from cosmic events, such as supernova or neutron star mergers, could provide valuable insights into their role in dark energy research. When massive stars explode, they release a flood of neutrinos that carry information about the extreme conditions of these events. By studying these particles, scientists can learn more about the universe's expansion and how dark energy might be influencing it. Similarly, gravitational wave detectors, which observe ripples in spacetime, could help us understand how neutrinos and dark energy interact on cosmic scales. However, studying neutrinos is no easy task. Their weak interactions with matter make them incredibly difficult to detect, requiring highly sensitive instruments buried deep underground to shield them from interference. Despite these challenges, experiments like the Ice Cube Neutrino Observatory and the upcoming Deep Underground Neutrino Experiment are pushing the boundaries of what we know about these ghostly particles. By capturing neutrinos from distant cosmic events, these projects aim to uncover new details about their properties and their potential connection to dark energy. As we continue to probe the mysteries of neutrinos, we may find that these tiny particles hold the key to understanding some of the universe's biggest questions. From their role in the early universe to their potential interactions with dark energy, neutrinos offer a unique window into the forces shaping our cosmos. By unraveling their secrets, we move one step closer to solving the puzzle of dark energy and the universe's accelerating expansion. With this in mind, let's turn our attention to the future of dark energy research, where cutting-edge technologies and ambitious missions promise to shed even more light on this cosmic mystery. As we look ahead, the future of dark energy research is brimming with promise, thanks to a new generation of groundbreaking missions and technologies. One of the most anticipated projects is the Euclid telescope, a European Space Agency mission set to launch in the coming years. Euclid is designed to map the large-scale structure of the universe with unprecedented precision, capturing the distribution of galaxies and galaxy clusters across billions of light years. By studying how these structures have evolved over time, Euclid aims to provide critical insights into the nature of dark energy and its role in the universe's accelerating expansion. This mission could help us determine whether dark energy's strength has remained constant or changed over cosmic history, offering clues to its true identity. Another key player in the quest to understand dark energy is the Vera Rubin Observatory, formerly known as the Large Synoptic Survey Telescope. Located in Chile, this observatory will conduct a 10-year survey of the night sky, capturing detailed images of billions of galaxies and tracking their movements over time. The sheer volume of data collected by the Vera Rubin Observatory will allow scientists to measure the universe's expansion rate with remarkable accuracy, shedding light on how dark energy influences the cosmos on the largest scales. Its observations could also reveal subtle distortions in the shapes of galaxies caused by dark matter and dark energy, providing a deeper understanding of their interplay. In addition to these large-scale projects, advancements in technology are opening new avenues for dark energy research. For instance, next-generation spectrographs, like those being developed for the Dark Energy Spectroscopic Instrument, or DESI, are enabling scientists to measure the redshifts of millions of galaxies with incredible precision. These measurements help map the universe's expansion history and provide valuable data on dark energy's effects. Similarly, gravitational wave detectors, such as the Laser Interferometer Space Antenna, or LISA, are poised to explore how dark energy influences the behavior of spacetime itself, offering a unique perspective on this cosmic mystery. Artificial intelligence and machine learning are also playing an increasingly important role in dark energy research. With the vast amounts of data generated by these missions, AI algorithms are being used to identify patterns and anomalies that might otherwise go unnoticed. These tools are helping scientists sift through complex datasets, uncovering hidden connections between dark energy and other cosmic phenomena. As these technologies continue to evolve, they could revolutionize our ability to analyze and interpret the universe's most elusive secrets. The future of dark energy research is not just about technology, though. It's also about collaboration. Scientists from around the world are coming together to share data, resources, and ideas, creating a global effort to tackle one of the greatest mysteries in science. From space-based telescopes to ground-based observatories, from theoretical models to cutting-edge experiments, the combined efforts of these projects are bringing us closer than ever to understanding dark energy's true nature. As we stand on the brink of these exciting discoveries, it's clear that the next decade will be a transformative period for cosmology, with missions like Euclid and the Vera Rubin Observatory leading the charge, and with new technologies and collaborations pushing the boundaries of what's possible. We are poised to unlock some of the universe's deepest secrets. The journey to understand dark energy is far from over, but with each new discovery, we move one step closer to unraveling the mysteries of the cosmos. Now, let's explore how artificial intelligence is revolutionizing the way we study dark energy, offering new tools and insights that could reshape our understanding of the universe. As we venture into the next frontier of dark energy research, one of the most exciting developments is the growing role of artificial intelligence and machine learning. These cutting-edge technologies are transforming the way scientists analyze the vast amounts of data generated by modern telescopes and observatories. With the universe expanding at an accelerating rate, the sheer volume of information collected from galaxies, supernova, and cosmic structures is staggering. Traditional methods of analysis simply can't keep up, but artificial intelligence is stepping in to bridge the gap. Artificial intelligence excels at identifying patterns and anomalies in massive datasets, tasks that would take humans years to complete. For example, machine learning algorithms are being used to sift through images from the Vera Rubin Observatory, pinpointing subtle distortions in galaxy shapes caused by dark energy's influence. These distortions, known as weak gravitational lensing, provide crucial clues about how dark energy interacts with matter on cosmic scales. By automating this process, artificial intelligence allows researchers to focus on interpreting the results rather than spending countless hours manually analyzing data. Another groundbreaking application of artificial intelligence is in the field of cosmological simulations. Scientists use supercomputers to create virtual universes, modeling how dark energy might behave under different conditions. These simulations generate enormous amounts of data, and machine learning algorithms are now being employed to extract meaningful insights from them. For instance, artificial intelligence can help identify which theoretical models of dark energy best match the observed behavior of the real universe, narrowing down the possibilities and guiding future research. Artificial intelligence is also playing a key role in the analysis of gravitational wave data. Events like neutron star mergers produce ripples in spacetime that carry information about the universe's expansion. Machine learning algorithms are being trained to detect these signals more efficiently, even in noisy datasets. By improving the accuracy of gravitational wave observations, artificial intelligence is helping scientists probe the relationship between dark energy and the fabric of spacetime itself. Perhaps one of the most promising aspects of artificial intelligence in dark energy research is its ability to uncover unexpected connections. By analyzing data from multiple sources, machine learning algorithms can reveal correlations that might otherwise go unnoticed. For example, artificial intelligence has been used to explore the relationship between dark energy and the distribution of cosmic voids, vast regions of space with very few galaxies. These voids are thought to be influenced by dark energy's repulsive force, and machine learning is helping scientists understand how they evolve over time. As artificial intelligence continues to evolve, its potential to revolutionize dark energy research is immense. From automating data analysis to uncovering hidden patterns in the cosmos, these technologies are providing scientists with powerful new tools to tackle one of the greatest mysteries in science. The collaboration between human ingenuity and machine intelligence is opening up unprecedented opportunities to explore the universe and uncover the secrets of dark energy. With each new discovery, we move closer to understanding the forces that shape our cosmos. Now, let's turn our attention to the philosophical implications of dark energy, exploring how this mysterious force challenges our understanding of reality and humanity's place in the universe. As we delve into the profound mysteries of dark energy, it's impossible to ignore the deeper philosophical questions it raises about the nature of reality and our place within the cosmos. Dark energy, this invisible force driving the universe's accelerating expansion, challenges not only our scientific understanding but also our philosophical perspectives on existence itself. What does it mean for humanity to live in a universe dominated by such an enigmatic force? And how does this reshape our understanding of reality? One of the most striking philosophical implications of dark energy is its reminder of how little we truly know about the universe. Despite centuries of scientific progress, dark energy remains a mystery, representing a vast unknown that humbles even the most advanced theories. This realization invites us to reflect on the limits of human knowledge and the possibility that there are aspects of reality that may forever remain beyond our grasp. It's a humbling thought, but also an inspiring one, as it underscores the endless potential for discovery and the boundless curiosity that drives us forward. Dark energy also forces us to reconsider our place in the universe. For much of human history, we've viewed ourselves as central to the cosmic narrative, whether through religious or philosophical frameworks. Yet, the discovery of dark energy reveals a universe that operates on scales and principles far removed from our everyday experience. The vast majority of the universe is made up of dark energy and dark matter, leaving the familiar matter we interact with, stars, planets, and even ourselves, as a tiny fraction of the cosmic whole. This shift in perspective challenges us to rethink our significance and purpose in a universe that seems indifferent to our existence. At the same time, dark energy raises questions about the nature of reality itself. Is the universe fundamentally comprehensible, or are there forces at play that defy human understanding? The fact that dark energy remains so elusive suggests that our current frameworks for understanding reality may be incomplete. This opens the door to philosophical debates about the nature of knowledge, the limits of science, and whether there are aspects of the cosmos that are inherently unknowable. Another intriguing philosophical angle is the concept of fine-tuning. The value of dark energy appears to be precisely calibrated to allow for the existence of galaxies, stars, and life as we know it. If dark energy were even slightly stronger or weaker, the universe would look drastically different and life might not have emerged at all. This raises profound questions about why the universe seems so finely tuned for life. Is this simply a cosmic coincidence, or does it point to something deeper, perhaps even a multiverse where countless universes exist, each with different physical constants? Ultimately, dark energy invites us to grapple with the big questions. What is the nature of reality? What is humanity's place in the cosmos? And what does it mean to live in a universe that is both vast and mysterious? These questions may not have easy answers, but they remind us of the beauty and complexity of the universe we inhabit. As we continue to explore the mysteries of dark energy, we're not just uncovering scientific truths, we're also deepening our understanding of what it means to be human in an ever-expanding cosmos. Now, let's shift our focus to the role of citizen science in dark energy research, exploring how everyday people are contributing to one of the greatest scientific endeavors of our time. Now, let's turn our attention to an exciting and often overlooked aspect of dark energy research, the role of citizen science. While professional astronomers and cutting-edge telescopes play a crucial role in uncovering the mysteries of the cosmos, everyday people are also making significant contributions to our understanding of dark energy. Projects like Galaxy Zoo are empowering amateur astronomers and curious individuals to participate in one of the most profound scientific endeavors of our time. Galaxy Zoo, for example, invites volunteers to help classify galaxies by analyzing images captured by telescopes. This might sound simple, but it's a task that requires human intuition and pattern recognition, skills that even the most advanced algorithms struggle to replicate. By sorting through vast amounts of data, citizen scientists are helping researchers identify patterns and anomalies that could shed light on how dark energy influences the distribution of galaxies across the universe. It's a remarkable example of how collective effort can amplify scientific discovery. What makes citizen science so powerful is its ability to harness the curiosity and enthusiasm of people from all walks of life. You don't need a degree in astrophysics to contribute. All you need is an interest in the cosmos and a willingness to learn. This democratization of science not only accelerates research, but also fosters a deeper connection between the public and the scientific community. It's a reminder that the quest to understand the universe is a shared human endeavor, one that transcends professional boundaries. Moreover, citizen science projects often lead to unexpected breakthroughs. In the case of Galaxy Zoo, volunteers have discovered rare and unusual galaxies that might have otherwise gone unnoticed. These findings provide valuable insights into the large-scale structure of the universe and how dark energy shapes it. By involving a global community of observers, researchers can analyze data on a scale that would be impossible for any single team to achieve alone. The impact of citizen science extends beyond data collection. It also inspires a new generation of scientists and science enthusiasts. By participating in projects like Galaxy Zoo, people gain a first-hand understanding of the scientific process and the thrill of discovery. This engagement can spark a lifelong passion for astronomy and cosmology, ensuring that the pursuit of knowledge continues to grow. As we look to the future, the role of citizen science in dark energy research is only set to expand. With the advent of more powerful telescopes and increasingly complex datasets, the need for human input will remain vital. Projects like Galaxy Zoo are paving the way for a collaborative approach to science, one that brings together professionals and amateurs in the shared goal of unraveling the universe's deepest mysteries. With this in mind, let's now explore the ultimate mystery of dark energy, a question that continues to challenge scientists and philosophers alike, and one that may hold the key to understanding the fate of the cosmos itself. Now, as we arrive at the final chapter of our exploration, we confront the ultimate mystery of dark energy, a puzzle that stands at the very heart of modern cosmology. Despite decades of research and countless breakthroughs, dark energy remains one of the most profound enigmas in science. Its elusive nature challenges our understanding of the universe, pushing the boundaries of what we know and what we can imagine. At its core, dark energy represents a fundamental question about the fabric of reality. Why is the universe expanding at an accelerating rate? What force drives this expansion, and how does it interact with the cosmos on the largest scales? These questions are not just scientific curiosities, they are keys to unlocking the deepest secrets of existence. The resolution of the dark energy mystery could reshape our understanding of physics, cosmology, and even the nature of time itself. One of the reasons dark energy is so perplexing is that it defies our current models of the universe. The cosmological constant, a leading explanation, suggests that dark energy is an inherent property of space itself. Yet, its predicted value differs from observations by an astonishing margin, leaving scientists to wonder if we're missing something fundamental. Alternative theories like quintessence or phantom energy offer intriguing possibilities but remain speculative. Each hypothesis raises new questions, deepening the mystery rather than resolving it. The implications of solving this mystery are staggering. If we can uncover the true nature of dark energy, we might finally understand the ultimate fate of the universe. Will the cosmos continue to expand forever, leading to a cold, dark heat death? Or could dark energy grow stronger over time, tearing apart galaxies, stars, and even atoms in a catastrophic Big Rip? These scenarios are not just theoretical, they are potential futures shaped by the behavior of this enigmatic force. Moreover, the resolution of the dark energy mystery could bridge the gap between the quantum world and the cosmos. Dark energy might be linked to the energy of empty space or the quantum vacuum, suggesting a connection between the smallest particles and the largest structures in the universe. Unraveling this connection could lead to a unified theory of physics, one that reconciles the laws governing the microscopic and the macroscopic. But perhaps the most profound aspect of this mystery is what it reveals about our place in the universe. Dark energy reminds us that despite our advancements, there is still so much we don't know. It humbles us, inspiring awe and curiosity in equal measure. The pursuit of understanding dark energy is not just a scientific endeavor. It's a testament to humanity's unyielding desire to explore, to question, and to discover. As we conclude our journey through the 25 mysteries of cosmic dark energy flow, we're left with a sense of wonder and anticipation. The answers may still be out of reach, but the quest to find them continues to drive us forward. Every observation, every experiment, and every new idea brings us one step closer to unraveling the universe's greatest secrets. And in that pursuit, we find not just knowledge, but a deeper connection to the cosmos and to each other. So, as we look to the stars and ponder the mysteries that lie beyond, let's remember that the journey of discovery is never truly over. The universe is vast and its secrets are infinite. But with curiosity, collaboration, and determination, we can continue to explore, to learn, and to marvel at the wonders of the cosmos. Thank you for joining us on this incredible journey, and who knows? Perhaps the next great discovery is just around the corner. Don't forget to like, subscribe, and hit the notification bell to stay updated on our explorations of the universe's greatest mysteries. Until next time, keep looking up as we bring our exploration of the 25 mysteries of cosmic dark energy flow to a close. It's worth reflecting on the profound journey we've taken together. From the accelerating expansion of the universe to the enigmatic nature of dark energy itself, each mystery has revealed just how much we still have to learn about the cosmos. These questions aren't just academic, they touch on the very fabric of reality, challenging us to rethink our understanding of space, time, and existence. The implications of these mysteries extend far beyond the realm of science. They remind us of the boundless curiosity that drives humanity forward, pushing us to explore the unknown and seek answers to questions that once seemed unanswerable. Whether it's the fate of the universe, the connection between dark energy and the quantum vacuum, or the possibility of a multiverse, each discovery brings us closer to understanding our place in the grand tapestry of existence. But perhaps the most inspiring aspect of this journey is the realization that the universe is full of surprises. Every observation, every experiment, and every new theory opens up new avenues of exploration, reminding us that the pursuit of knowledge is never truly complete. The mysteries of dark energy are not just challenges for scientists, they are invitations for all of us to stay curious, to keep asking questions, and to marvel at the wonders of the cosmos. So, as we conclude this exploration, let's leave you with a question to ponder. What if the answers to these mysteries are closer than we think? What if the next great discovery is waiting just beyond the horizon, ready to transform our understanding of the universe once again? The journey of discovery is far from over, and each of us has a role to play in unraveling the secrets of the cosmos. Thank you for joining us on this incredible adventure through the mysteries of dark energy. If you've enjoyed this journey, don't forget to like, subscribe, and hit the notification bell to stay updated on our explorations of the universe's greatest enigmas. Until next time, keep looking up, stay curious, and remember the universe is full of wonders waiting to be discovered. Who knows, the next great mystery might just be one question away.